Oh, this is a camera.
It's okay, it's on top of us.
Okay.
I tried to find a place you can leave if you want to leave. I need to see.
You can children about the site because he said I'm actually weird and wiki. Children interesting in my wiki.
Yeah.
As soon as I catch them.
Yeah.
Okay.
Funny.
He said that he studied MIT, Stanford, all around him he chose computer.
Really?
Yeah.
Did he say why?
But he said, yeah.
What did you say? Very sad. What was his subject when he spoke last time? Engineering.
Before I didn't know engineering so interesting. I saw it's very boring. Now it's different. You make so much interesting.
But this says School of Computer Science.
Yeah.
I think engineering is different from computer science. Maybe not. Maybe I don't understand properly. Because there are many different kinds of engineering. You know, they build a bridge, but they also make robots. Then also biology, bioengineering.
Yeah, bioengineering recently before was engineer always building a bridge that looks like it's Buoys. Now it's like we developed course the medical.
Yes.
So that's much more interesting.
Yeah, I think so too. Yeah, but they're probably engineering students or computer science students. Not Jade.
I was in the session. One boy said, I'm the freshman this year. I'm interested in some kind of project, but I couldn't find my red course. Then he said, the answer is because here, this college is called different subject. He said, whatever you need, coming to two, one is finished.
One is what?
Dean of the department.
Oh, dean.
Another is the global relationship said, coming to us, what you interested in. Maybe we can develop some course. That's very good.
But you know, Jade picked this place because it's small. And she picked this place because she said the administration, very quick. They listen and they do something. Very quick. Yeah, but now she comes here and so far she didn't use. But she just started. So let's wait, you know? Interesting. Lots of flexibility. You can, the business school, if you join, they take about 15 students every year who transfer from other parts of Carnegie Mellon. And they're making the school bigger. They're taking more students and they're also building it. They are wealthy. They are the wealthiest college in Carnegie because all the businessmen give money. And they gave me a list of. I'll show you. It's very impressive. I will. I was waiting to talk to her, but I show you one or two small things.
They said that for Jade department, every year 16% transfer to
Economics?
No, it's the Dietrich 16%.
1.6 or 6.0?
1.6. They said coming to Dietrich, people doesn't know what you're doing.
Right. Here's the salary. Maximum salary. This is their jobs that they got here last year. Here's the maximum salary, $110,000. Minimum salary, $40,000. Mean is exactly in the middle. And median means when you put a weight, how much above, how much below. This is the most important. $70,000. You should understand that for the United States, for a family of four, usually the income is 51, 52, 53,000. This means for one person in the business school, they're getting more.
But this last one is like the graduate.
No, no, no.
It's undergraduate.
Only undergraduate. This is only undergraduate. This is what happens after you graduate from the undergraduate. Not graduate. So that's very good salary. Then they said, business, you take a minor, everybody takes a minor, and it has to be from outside business. And the dean is there, and he said, we want you to do something completely different. Do music, play the piano, do something else, do engineering, nothing with business. We want to have a general person, not boring person who only does business. Very good. And they said, you have 50 choice, 50 minors, big choice. He said, if you're studying business technology, it means information, don't take statistics for your minor. Take something completely different. Then the next thing they said is, if you don't know, these are the areas you specialize. This is computer information. This is Wall Street. This is how to be your own business, small business. This is new, and this, I think from what you're talking about, art, graphic design is part of Nikki's school. It's a new area. It could be very interesting to deal with. How to present your information. To speak in public and to present and make colorful, very good.
I think the Jane Council for the business might have to go the second.
Let me explain. This is also very good. This is how to actually produce things and how to be a consultant, your own business consultant. And this is what Jade said, marketing. For me, it's the most boring. And like what you said, also low salary. Yeah. But this is interesting. You can register for this. This is for people who want to take two areas. So I'm explaining two of these areas, plus minor. So if she insists to take, I don't think she should do this. She should do this, and then she should do this, which is very solid, or this, which is very solid. She should do, so you can, if you're really enthusiastic, but you're not quite sure, you can do two. So this one, general manager, you can do two. I would do this because it's art, very lovely.
Okay.
And
all right, thanks everyone for coming. Am I on? Thanks everyone for coming. It's a pleasure to be here today on this beautiful day here at Cayley Weekend. My name is Nathan Urban. I'm the interim provost here at Carnegie Mellon, and it's my pleasure to get things started today with this fantastic panel of experts. So as you know, we're all here to celebrate a really important event in the 25th anniversary of the founding of the School of Computer Science. And I'm sure many of you know that Carnegie Mellon, computer science at Carnegie Mellon began well before that, really in the 1950s, when some real pioneers in the field in the form of Alan Newell, Herb Simon, began to think about this new technology and the potential impact for this new technology, not just narrowly in the context of a small set of problems, but very broadly across many areas, and how this would impact the future of the country, of the world. And this sort of broad view of computer science really has been very important in influencing the direction that computer science has taken here at Carnegie Mellon. It includes, of course, many areas that were at the time unforeseen. The whole development of the internet and the World Wide Web, the importance of big data that is really just now coming into clear focus, what that will mean for us and as we go forward. The interactions between humans and computers, and really down to the fact that probably 90% of the audience today has a very powerful computer in their pocket that can do many, many things for us that we're increasingly reliant on for our daily life. One area that was recognized very early by some of the pioneers here at Carnegie Mellon that was important was the area of robotics. And clearly, this is an area of increasing importance, this intersection between computer science, engineering, and design that is poised to really transform the world over the next few decades. And since 1979, when the Robotics Institute was founded, Carnegie Mellon has been pushing the forefront of that with our own Raj Reddy here as one of the very early visionaries in that area. But it was 25 years ago, in 1989, that the foundation of the founding of the School of Computer Science happened. One of my predecessors as provost, Angel Jordan here, was one of the leading forces in making that happen. And as I was walking over, I ran into him, and he mentioned the level of concern and opposition that he experienced to this event, which now, in retrospect, looks like a brilliant stroke of genius. And I think that we have visionaries like Raj and Angel to really thank for putting Carnegie Mellon where we are today in this area. So maybe we can just take a moment.
I can't hear a word you're saying.
So the history is wonderful to reflect on, and I think part of what we want to do today is think about not the history but the future. Think about the next 25 years, to some extent in computer science overall over the course of this weekend, but right now the next 25 years specifically in the area of robotics and how it is that will come to shape our future. I'm really excited to hear the panel talk about some of these areas. And so I'm going to get out of the way here very quickly and let the panel do its work. But before that, I wanted to introduce the person who will be moderating that panel, Carnegie Mellon Professor Howie Choset. Howie, who prefers to be called the dashing Howie Choset, I'm told, is a critical member of the Robotics Institute faculty, and one of the many things for which he's known is the creation and development of snake robots and their use throughout many different applications, including, I learned this morning, the exploration of prairie dog holes. Now, if you can be a faculty member at a incredibly prominent university like Carnegie Mellon and do things that are as interesting and fun as exploring prairie dog holes, you've got a great life. So with that, and be dashing. So with that, Howie.
So I think everyone here knows of the Robotics Institute. I don't think we need to give, at least to this audience, a broad introduction of what's going on. Look at all the things we do. It's great. The question I have is, who here likes robots? Just raise your hand. Who likes robots? Very proudly. Not good enough. Let's look at our founder, one of our two founders, Andrew Carnegie. He's famous for this quote, "My heart is in the work. My heart is in the work." The word "my" becomes an I. The heart, that heart symbol. The word robot comes from Carol Chapek's play. The word robot means work, drudgery, from Rossum's Universal Robots. So Andrew Carnegie predicted this. So now I'm going to ask again, how many of you love robots? In a platonic way, okay? I'm going to ask again, how many of you really love robots? Okay, so to show your admiration for these devices, if you look under your chairs, there's a black ribbon to your right. Pull the black ribbon out. Maybe the first, yeah. Except for the first row, sorry. We'll get you guys one later. me give one downhill. I'll give you one later. Yeah, let's do downhill. Oh, yes. Okay, good. Yeah, okay, so put the buttons on. You all love robots, right? You have a button saying it. You can keep the button. Okay. Question is, what's a robot? Okay. A lot of people, when they think of a robot, they have this humanoid robot form. And depending upon the kind of person you are, the friendly C-3PO or the Terminator, you could figure out who you are from that. But the thing is, we at the Robotics Institute, we're defining what a robot is. Okay? This is not a robot. This is the director, Matt Mason. Right. But look at the varieties. We have snakes, dogs, robots that balance on balls, robots that have 8 legs that climb into volcanoes, look for meteorites. This is an educational robot based on the Mars rover. Our software is on the Mars rover right now. We have a robot receptionist, who I might add takes breaks. We have robots that deliver snacks. Okay? We just do so much in robotics. Now, I think it's important to see where the Robotics Institute fits in on the org chart, because sometimes it's a little bit confusing to some of us. So here's Carnegie Mellon. It's a university. And like a university, it has many schools, more than I listed here. Sometimes we call these schools colleges. So we have an engineering college, a business school. And then here is the School of Computer Science, one of our founders. Within the School of Computer Science, we have a handful of departments. Sometimes this gets confusing. This is the computer science department in the School of Computer Science. So when you say you're in computer science, sometimes it's ambiguous. But let's look at the Robotics Institute. Founded 35 years ago. Nathan already acknowledged our founders, but I personally would like to express my gratitude again to both Raj and Hal Jordan, two of the 3 founders of the Robotics Institute back in 1979, 35 years ago. I'm just curious, how many here are under the age of 35? Interesting. So we have a great debt of gratitude. You know, this department, this institution that they created has affected so many lives, both in terms of their professions as well as the professions affecting other people's lives. The name Robotics Institute sometimes connotes research institute only, but this is an honest-to-goodness department within the School of Computer Science at Carnegie Mellon. We have the first PhD program that started in 1989. We now have a couple of master degrees. In fact, now we have an undergraduate degree in robotics. It's a second degree. By the way, if you were to remove all of the applied research that the Robotics Institute does, remove all the basic research that we do, and remove all of the university education that we do, we still have the largest K-12 educational footprint anywhere else in the world. Some of you may have heard of US First or FIRST. Our department sponsors 3 teams. One of them is an all-girls team, Girls of Steel. And they've gone to the nationals all 3 years they've been here. But it's just amazing. It's the educational impact in robotics that we've had. In terms of size, there's about 600 people in the Robotics Institute. We expect that number to approach 700 by the end of next year, because now we're starting to count undergraduates. It's an interesting place in that 2/3 of the faculty are actually research faculty. These are professors who bring in 12 months of their salary, don't teach, and they don't get university tenure, and they couldn't be happier than ever. It's an interesting culture. If you were to come into one of our meetings, at other universities, research faculty tend to be second-class citizens, not in the Robotics Institute, not in the School of Computer Science. They're first-class citizens. These first-class citizens who are research faculty, who don't get tenure, voted on my tenure case. It's just amazing. Lots of technical staff. And this $100 million here, that the annual research budget as of this year or last year, it seems like a big number because it is a big number, but that's grants that all of us have brought in to support our enterprise. Okay, so it's a very tedious process. We're the first, we're the biggest, and we're also the best. So advisory boards, which tend to be very adversarial, not adversarial, still say that we are the unquestionable world leader in robotics. Everywhere we are leading. In Washington, D.C., in the lab, out in industry, we are the leaders. Okay? If you ever see anything on the news or on TV that's about a robot, it's either one of ours or it's one of our former students who went off to another school that has a really good media program. So I'm happy today to be part of this panel, and we've picked these four great researchers. I'm going to introduce them one at a time, and if they can come sit at the table, that would be great. Yasser Sheikh, he's an associate professor in the Robotics Institute, specializing in all sorts of things that have to do with robot vision. Please. Kevin Dowling, oh, let's applaud for him. Kevin Dowling is one of our alumni. Yeah, I get the Greek or the Latin wrong. One of our alumni. He worked in the Field Robotics Center with Red Whitaker a long time ago. He went off and started working with a variety of companies, and now he's back in Pittsburgh working for 4Moms. Kevin? Nathan Michael, he's an assistant research professor who does all sorts of great acrobatic things with quad rotors. A lot of you have seen the recent popularity of quad rotors. A lot of that work stems from what Nathan did when he was a PhD student and is continuing to do here at Carnegie Mellon. Nathan? James Goslin, another one of our graduates, he says he got in on a coin toss to Carnegie Mellon. So I guess the coin landed the right way for us. He's the founder of Java. He wrote Emacs, and now he's, I think he loves robots. I gave him a butt. And Nathan already introduced me. So what we're going to do now is the five of us are each going to take turns giving a 5-minute presentation. And after that, we'll open things up for questions. And if none of you have questions, I'll start asking questions. OK, so Yasser, you're first. Do you want the clicker?
Yes, thanks. All right, thank you, Howie. So I was asked to give a quick, brief introduction of myself, and then I'll talk a little bit about vision and robotics at the tipping point. The wrong way. So my research work is in computer vision, which is the enterprise to make machines see, right? The particular thing I'm interested in is getting machines to see humans and human interactions the way we do, right? We collaborate and partner with other people. We form relationships with them. We pick up not just on gross things like faces and recognize people and friends, but we also pick up on hundreds of thousands of subtle, slight gestures that really define how we interact with other people. And machines don't do that, right? Machines can't see, and they're not able to perceive what other people are doing, and hence we can't form good collaborative partnerships with machines yet. This is one of the projects that I've worked on. It's called the Panoptix Studio. It's in the basement of Newell Simon Hall. It's this dome-shaped, what Howie likes to call the igloo, but it has 500 cameras spread out all over the surface of the dome, and it is probably the most densely sensed space in the world, right? And what we can do in this is reconstruct any activity in quite precise detail. So this is just a freeze frame, and then we can render it from any particular perspective. But more importantly, what we're able to do is measure not just the structure of things, but also movement, right? So here's a baseball swing, and we're able to reconstruct hundreds of thousands of points from these 500 cameras. So these are all the cameras. This is what 500 views of anything look like. And then you may have seen in special effects in movies people wearing these ping pong balls. We're able to do that without any markers whatsoever. And just to give you a sense of how free and open the measurements are, you can see confetti, lots of movement. Every point here is reconstructed independently. Okay. The purpose for this, this is a project in motion. The purpose of this is to actually sense in the highest level of detail social interaction. So what I'm going to show you is some measurement of lots of points in the body, and these searchlights are actually the gaze direction of people in the space. Okay. So that's just a quick introduction to myself and some of my work. But now let me talk to you a little bit about vision at the tipping point. So I presume the reason why I was asked to go first is because in the classic robotics pipeline, perception, cognition, action. So perhaps perception, I'm representing that. What is computer vision? I think the most important thing to talk about in vision is to say what it isn't. Computer vision isn't about processing just pixels. The purpose of computer vision is to use images to infer something interesting about the world behind the images, right? That's the key challenge. And one of the most confounding things about vision is that it seems very easy, right? We do it so effortlessly that you would presume that this problem is extremely easy to solve. And one of our origin myths, there's a story of Marvin Minsky in the 60s where they were trying to plan a robotics project, and as an allocation of effort to vision, the perception part of the project, they allocated one undergraduate a summer project to solve vision quickly. I spoke with that particular undergraduate. His name is Gerald Sussman. Actually, I should say Professor Gerald Sussman now. He's a professor at MIT now. And he said, I'll quote, he said, after that project, Marvin Minsky said, the best way to learn about a difficult problem is to give it to an intrepid undergraduate who doesn't know enough to realize it's impossible. Absolutely right? I've used this trick often. It's actually quite true. So to give you a sense of how hard this is, the reason why it's hard is a lot of the processing we're doing in vision is happening subconsciously. We're not aware of it. Neuroscientists estimate somewhere between 30 to 60% of the brain is involved in vision processing, right? And this number, this interval is not because we don't know what it is, but because it's hard to segment out where vision ends and where the rest of the brain function begins. Okay, so after this kind of start in the 60s, another key landmark in the 60s was Professor Takeo Kanade, one of the leading thought leaders in vision, started work on face recognition as well in the 60s during his thesis. And Raj was very instrumental in bringing him to CMU, and he's led the vision charge since then. The 70s were largely engaged in realizing that this was a very large and difficult problem. And it actually ended largely in failure. There was a lot of effort and a lot of failure. Towards the 80s, I would say that's when the navel-gazing phase of vision began. It was realized that this is a very difficult problem, and we started looking at smaller and smaller problems in the hope of maybe solving these a little bit. When I started doing research in vision, maybe towards the late 90s, early 2000s, there was this sense I got at conferences where I think it can be best summed up by Marshall Eber, he's a professor here as well, that we all know vision doesn't work, right? This was the sentiment. And then slowly over the last decade or so, we've seen applications emerge. Takeo Kanade started the face detection problem in the 60s. Recently, you must have seen, not recently, but you've started to see face detection is solved. You see it on your cameras, you see applications and systems coming out. We've seen computer vision enter special effects. We've seen them enter many military applications as well, right? And so we've started in the last decade to start emerging from this navel-gazing phase of vision. And there is this real sense I get today. In conferences when you go, you feel like researchers have smelt the blood in the water. We feel like lots of long-standing problems are within striking distance where we're going to be able to solve them soon. And one kind of good indication of this is if you look at the average market cap of the companies that are investing in vision research today, it's skyrocketed in the last 10 years, right? Microsoft has always had a group. Google has had a group recently. Amazon is hiring and as a huge group at this point, Dropbox. And there are in fact a number of companies who I cannot name who are also in stealth mode and are building large capabilities in vision as well. Okay. And they're not looking at this simply as research. They're looking at this as really integrated into products as well. Okay. I would say there are three confluences of technological advances that have caused vision to start emerging and making this one of the most interesting periods in vision research. And I expect this will be a theme that we'll see throughout this panel. It's the improvement in data, not just in the size of data. People talk about big data, but the quality and diversity of data as well. Someone mentioned everyone has a computer in their pocket today, but we also have excellent cameras in our pockets, all of us, right? We're capturing data at huge amounts, huge rates. Someone estimated that 2/3 of all the traffic on the internet is video and images at this point. So it's a very exciting time in vision. We're really starting to see things happen. And I was asked to make a few I can't say the word, prognostication. It's a good thing I'm not doing speech research. Predictions into the future, forecasts. One is, I think we will quietly exceed human performance and perception very soon, right? Sensors can sense at higher resolutions and higher frame rates than people can. And the second is, I think I started by talking about perception, action, cognition as a pipeline. I think there's an illusion of separation between these three things, and that's going to break down in a big way in the next decade, which is that perception is not separated from cognition, which is not separated from action. These are, in fact, three concurrent enterprises, and they should be thought of in that way, too. And since we've started to see vision work, I think we're going to be welcomed back into the family of cognition and robotics, action, and see some real breakthroughs in that space. I shouldn't mention applications. I guess we'll discuss those. But I'd like to end to say it's a really exciting time to be in computer vision, and the applications that I look forward to in the next decade. It's just going to be great. Thank you.
Thank you. Where's the clicker? Oh, sorry. Hi, Kevin. Give it to Nathan.
I passed the baton on.
So I left Carnegie Mellon in 1997 after finishing my doctorate in robotics. Rick Whitaker was my advisor. Had a great time, but I went into industry because I wanted to create things that people used. And halfway through my thesis, I realized I didn't want to stay in academia. I loved it. It was incredibly fun here. I had more fun than almost any other point in my life. But I really wanted to build things that matter to people. So I went to a company which no longer exists. It was bought out by another company called PRI Automation, and they focused on the semiconductor industry. So they made the robots that move the chips and the wafers around in the fabs. Very expensive, high value, ultra clean. They couldn't fail because they're holding millions of dollars worth of these wafers at any one time. The wafer goes down, Intel calls you, you run. You jump as high as they say. It was a very challenging time. The semiconductor industry is notorious for its cyclic variations in business and so forth. And I had a really interesting opportunity come by a couple of years later, where a couple of CMU alums asked me to join and head up in engineering for a small company in Boston called Color Kinetics. It really started here in Pittsburgh, though, with a bar bet around the use of LEDs, light-emitting diodes, which are now ubiquitous in lighting. And Color Kinetics became the first company to use LEDs for illumination purposes as opposed to indications, like traffic lights or power devices on equipment, as one example. Color Kinetics grew very rapidly, went public, got acquired by one of the largest lighting company, the largest lighting company in the world at the time, Philips, in 2007. And I learned a lot of lessons there. That was my MBA, and I found that I really liked the business aspect of it and really enjoyed that. So instead of building technology per se, I focused more and more on building teams, on building products, and building companies. And that's what I've continued to do till today. A few years ago, I joined another company in Cambridge called MC10, which did wearable technologies. We made ultra-thin electronics and used them on the body and inside the body for medical purposes. I left just earlier this year and actually moved back to Pittsburgh. My wife and I and my son moved here from the Boston area to join a new company called 4Moms. And I want to show you the robots that they make. And I don't think that there shouldn't be any argument here, because this is a robot. It also happens to be a baby stroller. It's much more than that, because the devices and the wheels allow you to generate power to recharge the batteries. Oh, thank you, Jennifer. Allow you to recharge the batteries or charge your cell phone. There's a display on the device, an LCD display for the user that shows temperature, it shows distance, and it shows speed. It has cup holders, and it has all kinds of daytime running lights, which are LEDs, one of my favorite light sources. And it has lights on the bottom and a number of other features. These are premium devices, but they're now in a category which now sells not 1, not 10, not 100, but in the thousands. We have other products that utilize motion control and actuation and sensing that sell in the hundreds of thousands of units. And that's really rewarding. This is being used to hold probably the most precious cargo in our lives, babies, our infant daughters and sons. And these devices are robots, and I won't argue with you because it is. It has actuation, it has sensing, it has computation, it has user interfaces. What isn't a robot about this? It's absolutely a robot. And so what's happened, and these are the trends that Yasser talked about as well, in the confluence of decreasing cost of processors, the decreasing cost of motors and actuators and sensors, all of this has led to a phenomenal ability to be able to integrate this technology into anything else. This is a premium priced device, but there are many strollers in the market that are much more than this, and they don't have any of the capabilities that this one has. So you're starting to see that continued drive to lower the cost. But if we're going to argue that if robotics is at the tipping point, what are other metrics that we can use? And some might be just numbers and volumes. I've talked about one from 10 to the 0 to 10 to the 7. So 10 to the 7 is 10 million units. Well, iRobot has sold 10 million Roomba vacuums. There's still more than that, and they continue to sell more than that. That's a large number. It's a critical mass. It's an ability. And that doesn't even talk about things like, well, how far has something gone? Well, if we look at Google's driverless cars, which are not yet commercialized, but will likely be in the next decade or so, and those, interestingly enough, you can trace the lineage of that program all the way back here to CMU, where Sebastian Thrun and Mike Montemerlo and others began working on the autonomous vehicles here back in the 80s. And I was building those with Red Whitaker. So you can trace all of that. But they'll probably do in the next 12 to 18 months, probably 1 million autonomous miles, which is phenomenal because back in the 80s, we were doing centimeters and thought that was great. And we were doing that inside. We weren't on real roads. But by the mid-'80s, by the late '80s, we were doing highway speeds, and we were really moving along very quickly. So all of those trends show that this is going to continue, that we have that power and being able to do that. We can also look at things like the numbers. What's invested in robotics today? What does robotics revenue represent? Well, in 2012, there's about $12 billion worldwide revenues in robotics. It's not quite the full GDP of robotics, which is much larger, but it's predicted that that number will be in the order of $20 billion by 2016 or 2017 or so. So that number is growing. Is that a tipping point? Well, what about adoption or diffusion or saturation? We certainly haven't approached saturation, which is when the demand begins to fall. But we certainly are seeing an uptick in many robotic applications, and you'll hear some of those from the panel today here. So I think there's no argument that is robotics at the tipping point? I'm not sure, but it's happening now. That uptick is continuing. And the tipping point is typically defined as where the rate of progress increases dramatically. And I think the evidence you've seen here today, and you will see here today, and what you're seeing in the marketplace, what you're seeing in the world today, shows that that's happening. So we are at the tipping point, and I don't think there's any argument or discussion around that. Thank you.
My name is Nathan Michael, and I'll be talking about aerial robotics. Aerial robotics. A bad omen.
Let's see, he's good.
Seems the computer went to sleep. So. Okay, so aerial robotics is at the tipping point, possibly past the tipping point. How many of you have, for example, an AR drone that you work with or play with on a regular basis? You can go to the store and buy these right now. Many of you have seen this video, which is an advertisement for Amazon Air Prime. This is not a joke. This is a real thing happening. Amazon is doing this, and it's not just Amazon. Many other big companies are working on this type of problem. And we're looking at this in the very near term. You're talking about your Googles. Amazon is looking at cargo delivery. You have a variety of different larger companies investing in this domain. In fact, we're seeing exponential growth. In the last 5 years alone, we're starting to see an industry which was unheard of to one that's now approaching $10 billion. So we're looking at startup companies left and right, maybe 75 in the last year looking at this domain. At the same time, though, we have a satire on the bottom right, which is from Netflix, which is a response to this video. And it basically shows the reality that we live in. And that is that while these systems work reasonably well, they're not ready to deploy. So the question that we have to ask from an aerial robotics perspective is how we can enable these types of systems to really work in the world around us. Right. So what you're about to see is a drop-off delivery program. And so I wanted to comment on, actually there was a recent article by one of the faculty members in the Robotics Institute that talked about aerial robots as small. So there was a recent article that talked about how aerial robots would become like smog all around us, above us. When we looked up, we would see these systems flying over us, and we wouldn't really know how to interact with them. And we would also be concerned for our safety, for our privacy. There are these huge questions that we have to ask, and our legislature right now, from the FAA perspective, is advancing, but it's too far behind. So this area is growing so quickly that we're having to react to the technological advancement. There are so many applications in which aerial robots have impact. And you may say, well, why didn't this happen 10 years ago or 20 years ago? Well, aerial robots are fundamentally constrained in size, weight, and power. As the robots get smaller and smaller, their lifespans change. They need to be able to carry on board lower power, higher performance processing, higher performance processor or sensors at a smaller size. We're looking at a lot of questions here. And only in the last maybe 5 to 10 years has technology made it possible for us to pursue applications. For example, aerial manipulation and assembly tasks, mapping and inspection, remote sensing, precision agriculture, payload delivery, as the videos just showed, even things like innovative media. You're starting to see commercials, movies. The FAA has recently allowed Hollywood to actually use drones in filming of movies because it's safer, it's more effective. And so what we're seeing are aerial robots not only at the tipping point, but past the tipping point. But there is a question of how we can start to bring these into our everyday lives, start to trust them in terms of safety, trust them in terms of privacy. And as we do so, we need to think about how we can enable them with intelligence. So how we can connect perception and cognition to action. On the top left video that is being played, this is some work that I had done with some colleagues and students at the University of Pennsylvania about 4 years ago now, 3.5 years ago. The date there is the publication date. But what you're seeing there is autonomous flight in a motion capture arena. So we know very, very well, very precisely where the robot is at any time. And consequently, we're able to develop trajectories and feedback control laws that enable that system to fly very precisely and to maneuver through windows. And this level of performance is only possible in that instant due to this very expensive motion capture system that is in the laboratory. However, last year we showed these results. The motion capture system is turned off. And what you see on board there is, in fact, vision and perception running directly connected to the cognition and action. So this is a great follow-up to Yasser's remarks. What we're doing here is we're thinking about how it's actually perceiving the environment, connecting the action to the perception of the environment, and everything becomes one in this instance. And consequently, we're able to fly quickly. In fact, so fast that if you normalize with respect to, say, the fastest, largest scale helicopters, we're talking about multiples in terms of speed. So this system, for its size, is the fastest autonomous vehicle out there. But if we want to go outside of, say, the controlled environment, on the bottom left, you can see a system being deployed in a very small pilot experiment that actually occurred in an earthquake-damaged building in Japan. The robot was deployed off of a ground robot, so it's actually going to land on a ground robot. The ground robot will now carry it to another location, and it will continue to do so. And as it moves through the environment, it builds a map of that environment, and now we could use this map for something like inspection or search and rescue in the context of a disaster response. So the ground robot will now carry it off. What's interesting about this, though, is that we are now moving forward on this particular problem and working with the same colleagues in Japan to take this technology and push it through to an actual deployment situation. So we're now working to put these robots into the Fukushima Daiichi nuclear reactors. There are certain areas on the 4th and 5th levels of the buildings that are inaccessible to the ground robots. And we need to know what the radiation levels are, what the damage level is, and how one could perceive or in the future clean up that environment. Now, these are two separate robots, one ground, one aerial. If we wanted to, we could start thinking about multiple aerial robots. And here we have two. And if I showed the whole video, I would show more robots. So these are actually aerial robots that we've built right here at CMU. So it's completely custom. And we are able to have these systems communicate with each other, share information. If one robot were to die and fail, just crash, the other robot would be able to continue. They're able to operate just not only independently, but collaboratively, using the knowledge from each other in order to make decisions about how they move through the environment. So in about 20 seconds, the robots will start talking to each other. They'll share the maps. And now they have more knowledge than what they started out individually. And this scales very nicely. And it runs in real time. And the main point here, though, is that as we start to think about not just one of these systems or multiple vehicles concurrently operating in these kinds of challenging domains, we start to have an opportunity to pursue many applications that were previously thought as quite futuristic. So here is a video from a TV show. It's completely CGI. It's completely futuristic. Nothing in it is real. And what they're doing is they're walking into a building after a fire, and they open up a case. And they want a map of the rooms, the building, in order to be able to find specific items that are damaged and get a better idea of the scenario. And so here you see a team of small quadrotors flying through the environment, perceiving the environment, sharing information, and ultimately detecting what was the source of the fire. The interesting point here is that you would think that this is definitely the future. But in fact, I would say that we'll probably be able to do something like this in 3 to 4 years. We have smaller systems, we have the perception, we have the coordination. And so in this way, you look at it and you say, well, that's very futuristic, but actually it's quite now. And so I think aerial robotics is not only at the tipping point, but it's moving forward so dramatically, so quickly, that we're going to start to see these systems all around us every single day as we drive into work and these systems are inspecting bridges or buildings, looking at incidents in response to search and disaster, cargo delivery. We may actually see robots flying over our head dropping off packages in the very near term. I'll close there.
Hi, so I'm James Gosling. I graduated from here too many years ago. These days I work for a little company called Liquid Robotics, and we do robots in the ocean. An actual commercial company that actually deploys these things. And the ocean is a very unusual place to do robots. These robots don't look at all like what you would expect. They don't have wheels and arms and the rest of it. They've got sort of mechanism on the bottom that's got a bunch of wings, and then there's this umbilical cable that connects it up to the float at the top. And if you're near to shore, you can go swim with them, which is always fun. So this is how they work. So there's a piece that floats on top of the ocean that's about the size of a surfboard, that's got solar cells on top and a bunch of antenna mass. And there's this umbilical down to this wing rack. And the wing rack has these wings on it. And the wings just have a little pin that goes through and a hinge. And it's being pulled up and down because of the wave action. And so the wings generate thrust exactly the way the tail of a whale generates thrust. And the mechanism to generate thrust is extremely simple, extremely reliable, no electronic anything in it. But it's possible to make it be very, very strong. So the design point of these is to survive hurricanes. And we've been through dozens and dozens of hurricanes. In fact, there was a pair of hurricanes that went through Hawaii just a couple of months ago, and we had 13 vehicles underneath the hurricane. And when we do things like hurricane studies, we're really the only data source from underside a hurricane. We're the only thing that survives the underside of a hurricane. And you know, a lot of that comes from the unique sort of mechanical engineering in this thing. I mean, the company was founded by a mechanical engineer, and I sort of came along a few years later because they figured out that they needed software for this thing. And let's see if I can get the video to start again. So these solar cells provide power to computer systems that fill the hull. There's that gray knob on the top there. That's a satellite antenna, and we do most of our communications using the Iridium satellite network. It's a network standard called SBD. Costs us about $1 a kilobyte. Very different scale of networking, and a different scale of expense. So you have to think about networking very differently. But also, we end up being inside hurricanes. We cross oceans on a regular basis. We stay out at sea for months and months at a time. These things have to be incredibly robust. A lot of what goes on in the hardware is designing them to be robust. So there's a dramatic amount of titanium in there. Living with salt water is really, really hard. The software not only has to do the stuff you would normally think of, but there's, since these things are running without human control mostly, they have to be able to do things like dodge ships, so to not get run over. So the autonomous behaviors on these things get really, really interesting, and they do a fair amount of fault management. So things are always going wrong, and we do various things to cope with them. GPS units fail. They can often be fixed by rebooting or various other sort of poking at them. The only actuated thing on the whole device, there's a rudder down here, and that's the one and only thing with a stepper motor on it that we use to steer. Everything else that has to do with motion is not controlled by us. It's just the wings and the springs. So we've got the engine that doesn't stop. It just keeps going. So these things end up being used as platforms for sensors. You can put sensors on the top. The thing at the top with the little white blob, that's a weather station. We can put sensors down here. A lot of the times we tow sensors like this. So there's this cable that we go that's got sinkers and floats and sinkers and floats, and that gives you this sort of accordion pleat so that the sensor payload that we tow is in very smooth flowing water. So it's decoupled from the up-down motion, and it's just going very smoothly through. So lots of scientific instruments are happier when the water flowing around them is very, very smooth. We also don't go terribly fast. We usually go at about 1 knot to 1.5 knots. So it's like, sort of a leisurely stroll across the Pacific, which turns out to be just a perfect speed for most people's instruments. So what do we do with them? We act like weather buoys, for instance. You'd think that weather buoys are kind of normal and well understood. And they are. The problem is we need a lot more of them, and they're extraordinarily expensive. And you'd think weather buoys, why are they expensive? It's not the buoy that's expensive, it's getting it there. So if you want to put a weather buoy in the middle of the Atlantic, the ships to get out to the middle of the Atlantic cost about $150,000 a day. So if you break a $50 solar panel, somebody's got to go out and fix it, which is about a 10-day round trip. Do the math. You've just spent $1.5 million to repair anything, and every time you have to install one of these, you have to, it's sort of the same bill. There's a huge array of weather buoys around the equator. The last repair ship for them got defunded a couple of years ago. Thank you, Congress. So they're slowly going dark. And we're doing trials with NOAA right now for at least for the Tau array in the Pacific, because with our guys, you just sort of throw them in into the water, and they swim out to wherever you want. So they'll happily swim down to the equator from Hawaii. We do that all the time. And it's this ability to survive in extremely hostile environments that is really different about these things. The ocean is only occasionally like this. So we typically deal with like 20-meter seas. There's a distinction between swell, which is waves that are sort of long period and are sort of a long period accumulation of energy. And then there's chop, which is sort of energy that is sort of instantaneous coupling with the wind. So most of the bouncing that you see here is chop, but the larger ones are swells. We had an incident a few months ago where the sea was basically flat, almost no swells, and this bizarre freak wind came up that was about 150 miles an hour. So we ended up with ocean chop that was about 15 meters, 45-foot chop. So the thing about chop is that the frequency is much, much higher than swells, right? So the period from peak to peak was 6 seconds. So you've got a 45-foot wave being thrown at you every 6 seconds. Survive that. And we had three robots out in that particular storm. That one was exciting, and they all survived. There was a little more wear and tear than we would like. So there's now even more titanium in these things. We do pollution monitoring, because this is really just a platform for scientific instruments. So you can do all kinds of water chemistry measurements. We do a lot of sort of, white on white doesn't really work for text. Cutting and pasting is a bad idea. We do a lot of work with scientists on things like global warming studies. These guys were looking at mixture of CO2 from between the water and the air. We had nine of our robots up in the Arctic this summer. Very, very entertaining, working on a device that has a compass that close to the North Pole. Yeah, the electrical engineers all said, "Oh, the compasses, they'll work." And then all across the Arctic, 9 of these things got dropped into the ocean, and there's like none of the compasses worked. And so I got to spend 3 days trying to figure out how to navigate without a compass. And that was entertaining. And by that time, these guys are like sitting alone in the middle of the Arctic Ocean and Baffin Bay. And one of the great things you can do with Java is in a very safe way inject code into things. Really nice features there. There's like so many reasons. I love to be a user of the stuff that I used to build. But we were able to update these things on the fly, and they did really well, except for the one that got crushed between 2 icebergs. But we can count fish. We can talk to seafloor sensors like gravitometers, things that measure tsunamis, things that measure the shifting sands around oil pipelines, and it's often an excuse for me to go snorkeling. So thank you.
Howie, could you take a 1-minute break? Because there are a bunch of people standing in the back, and it's at least as uncomfortable for them as it was for me to maybe find seats.
Come into the front. There's plenty of seats in the front.
It's not as much fun sitting on the floor as it was when we were graduates.
Kevin, how much does one of these things cost me?
That's $849, but give me a call and we'll figure out something.
What about the rocker?
That's
Yes,
like
sir. Yes, sir.
Cool.
Yes, sir.
Yep.
So this video is not playing, it's just giving this. Is there a way you can make it play maybe in slide mode?
playing, but is it just?
No, it's supposed to be like snake robots.
It hold the slide for a while or not?
Okay, let's not go back to the beginning. Yeah, that's good. Yeah, I'll say play from there.
From here?
That's fine. It's the same problem as before. It's fine. So this is a video of a snake robot going very slowly. It's supposed to be moving. It's a nice still, but I can't figure out how to make the video go.
No, we have to see it play, right? That's the. Maybe step out of the.
Let's just step out of that. Professors.
We may need more help too.
Well, it's a Mac.
Where's the video? Is this one?
Yeah, try that. It's right there.
Let's give it a bit of time. I think it may be the same thing about taking a little bit.
All right, that sucks. Okay. So these still shots are snake robots. Here's an old snake robot.
So we're not seeing anything at this point.
You're not seeing anything?
You want to show a few?
Yes. If not, we'll just. All right, let's just skip it. Don't worry about it.
Mess with my machine.
Nope. That's okay. Let's just go to the next slide. So these robots, and there's tons of videos of these on websites all over the world. My group's website is biorobotics.org, and that's where we have lots of videos of these snakes. But what's good about these robots is, they look like snakes, and as such, they can thread through tightly packed volumes and get to locations that people and machinery otherwise can't access. In a sense, you can do minimally invasive surgery on structures. So an application that's near and dear to my heart is urban search and rescue. Can we provide a tool that rescue workers can use so they can locate victims who may be trapped in a void space in a collapsed structure? Because just locating those people, that really saves their lives, giving them hope that help is on the way. Bring them food, water, oxygen, that's icing on the cake. However, these tools, that kind of environment is very unstructured, it's very hard to maneuver through, and we're still just trying to figure out how to make that work in terms of building the robots as well as programming them. So if we just go to the next slide. That's not the next, this slide. So another application we did recently is archaeology. Archaeology in confined spaces is just like search and rescue, except everyone's been dead for 5,000 years, so there's no rush. Okay. What we did here, and I should acknowledge Maj Sakar was one of my colleagues who came with us on this trip, is the Egyptians, they lived here, and they wanted to trade with people in a city called Punt, so they carried their boats across the desert to the Red Sea, assembled them, and then sailed down the Red Sea, did their trading, came back, and then instead of carrying their ships back to the Nile, they disassembled them and hid them in man-made caves off the coast of the Red Sea, so this way they could save themselves a trip, hide the ships from the bad guys, come back, and this process went on for years. The problem is those caves they're very unstable. So we were asked by Catherine Bard, a professor at Boston University, to see if we can send our snake robots into these caves to locate further evidence of these ships. Now, when we went to Egypt this first time, it was a wonderful experience. I remember talking with Raj about this before I went. Our stuff was confiscated in the airport by the police or the military. And there was 4 days of, so Maj, he was at the Red Sea at the resort, while my student and I were in Cairo negotiating, and I don't speak Arabic. Maj does. But we negotiated 4 days, and in the end, we got the robots back, but there was a bribe. The question for you is, how much was that bribe? Any guesses? $20. First, this is priceless equipment. Okay? So you think about it, okay? So in the end, we didn't find anything, but we were lucky enough to meet Zahi Hawass afterwards, who sent us into these caverns underneath the Great Pyramid in Giza. It turns out there's a void space, mostly about the size of this room, filled with water. There's a little crevasse off to the side, and they don't know where it goes. So we sent our snake robots in there. The only thing is, we only had 45 minutes, and we went as far as we could in 45 minutes. We were supposed to go back, but then it wasn't. Other developments occurred in Egypt, which made it hard for us to go back. Actually, this summer we were in Turkey doing something similar. A question we're commonly asked is, are these robots biologically inspired? You know, yes, at a superficial level, you see a snake, and you can say, oh, let's try and copy these motions. But in our group, we kind of, will this video work? I want to acknowledge my colleague, Dan Goldman, at Georgia Tech. But in our group, what we do is we look at principles of biology. Instead of trying just to copy in one step, can we look at these fundamental principles? Dan, who's a biologist, he's interested in replicating and validating these principles on our robots. We, the robotics people, we're interested in enhancing the capabilities of these robots. So now, for the first time, actually in years, you know, in the 18 years I've been working on these robots, we are taking a serious look at biology to figure out how to make these mechanisms much more capable than just our raw engineering and intuition alone was able to. And I'm proud to say that Dan and I actually had a paper appear in Science yesterday on the first part of our work. We actually are starting to decode how sidewinders indeed locomote. It's kind of funny, because of our recourse to engineering intuition and an understanding of computer science, we were able to tell the biologists how the real snakes work. Dan actually believes he's telling us how to make robots work better, so we have this friendly conflict going on. That's okay, let's just go to the next slide. So this is a prairie dog. I think Nathan talked about this. Last week, we sent our snake robots into these prairie dog holes, mainly because some person at the University of Maryland, John Hoogland, is very charming, and he convinced me to do this. But it's amazing. You know, these holes are they're prairie dog made, about 3 to 4 inches in diameter, and here we are, you know, crawling through them, and we were actually able to make some discoveries about these prairie dog holes. For one thing, they don't understand the topology, how these holes connect or disconnect. They didn't even know where the prairie dogs went to the bathroom. We also discovered a nest, and we learned a little bit about how prairie dogs escape predators, because when the predators come down these holes looking for lunch, prairie dogs actually have emergency exits that are cleverly designed. So if they're being chased, they can take a quick 45-degree turn one way and then escape unnoticed. So the thing is, you know, prairie dog holes are fun, but you can imagine other kinds of confined spaces. So one of them, spaces into which we're trying to get, and I really hope this video works. Will it go? Are these nuclear power plants. So here, if you go to the website, you'll see videos of this. This is a nuclear power plant in Zwettendorf, Austria, that was built, and then the Austrians decided not to turn it on because they were afraid of nuclear problems. So now it's a training facility. And what we were able to do on our first try was go into this facility and send the snake robots into locations where conventional inspectors would not be able to access, even with their borescopes. They would have to take part of the facility apart. So this is nice. You know, we have a tool that inspectors can use. In fact, we were able to see things in this power plant that hadn't been seen in over 30 years. In fact, we found a defect. When they assembled the plant, they left some bolts behind in one of the pipes. So if they had turned the plant on, the bolts would have accelerated into the turbine and would have blown the whole thing up. So we found that. We left the bolts there because we didn't want to disturb anything. But that's OK. But the thing is, where I think these robots would be good in this industry is in the United States, we have a lot of spent nuclear waste. There's lots of it. In fact, by 2020, we will run out of places to put it. Right now, we have these dry cast storage containers. And I was approached by a couple of organizations, DOE and EPRI, because they have some of them on the Chesapeake Bay And they put these canisters that have the nuclear waste on the Chesapeake Bay because they figured the boats would come in, it's convenient, pick them up, take them to wherever they were going to go. So the thinking was this is a good place to put them because it's easy. But now they're rotting and decaying and they're on the Chesapeake Bay. There's also 1,500 of them. Okay, so that's a problem. Okay, and none of us know what the insides of these canisters look like. So we're in the process of trying to work with the DOE and this other organization called EPRI to send our robots into these canisters to assess their current status. Because at this point in time, they have now lived longer than they were designed for. Okay. I think at this point, I ran out of time, and I would be hypocritical if I went over my time and forced everyone else to stay under their time. So what we'll do now is we'll do the panel part of our presentation. So with that, I thank you for your attention. So we have some prepared questions for the panel. We prepared some questions for the panel that I'm happy to ask them. But I figured you've heard us talk for long enough. So let's open it to the audience first and see if anyone has questions. And if people are slow in thinking of questions, we'll just throw random ones in. So any questions for us?
How much was the bribe?
4 days of negotiations. I went to the embassy, and they told me about other bribes. So the embassy, our embassy, said, listen, we can't tell you this, but the truth is you got to bribe these guys. So on one occasion, there were these whale bones that were Egyptian whale bones that we were bringing back. Okay, they were theirs. And that was a $20,000 bribe because the Americans didn't want to lose the whale. So I was prepared for thousands of dollars. Okay, and finally, in my trying to figure out, again, I don't speak Arabic. I had someone who spoke Italian and Arabic with me that we met, and I speak a little bit of Spanish. So between the Spanish and the Italian and the Arabic. So finally, the two soldiers looked at me and said, it's time for the bribe. And they looked at me and said, $5. And I looked at them and thought, for each of you? And they looked at each other like, we have a fool here. It was $6. Okay? So we pack up the equipment, we go outside, we're looking to make sure everything's fine, and a police officer comes by, and I'm thinking, I'm going to lose another $1. So it was $6, and I was reimbursed. So questions? So if you have questions, why don't you start to line up by the microphones? This way we can go one after another. Right. So I saw there was someone else in the back with a question. Yes?
Thank you guys so much for coming. This has been a really enlightening talk. I have a friend who is a roboticist, and her main grumble is that people expect a really long life out of these robots, and in actuality, they have errors and mess up every day or so, and that the future robotics, this amazing future we have, is maybe not quite possible yet because we just don't have robots that can last and can work properly for an extended period of time. And I was just wondering if you guys had any insights onto maybe how that's changing or strides that are happening in that area. Thank you.
So I'm probably the only one that actually in this that makes robots that last. So our robots are typically at sea for many months, and go through many storms. And if something goes weird, there isn't a lab technician on the other side of the room to fix them. And so it's a combination of unbelievably painstaking mechanical engineering. And when you look at the control software on our robot, it's like 10% interesting stuff and 90% staying alive. The effort that goes into going from it works to it works for a really long time and doesn't screw up ever is an astonishing amount of work. But you can get there. It's just labor.
Yeah, we have units commercially for sale that we test for months at a time, and the reliability engineering is a huge part of it. Working in the lab once is not a reliable product. Working in the field for months or years is a hard problem and solvable. I mean, you engineer the hell out of it, but it takes a lot of time and a lot of effort to do that.
Okay, thank you. Let's do this side of the room.
Yeah, hi. I just wanted to ask, how long into the future might it take to come up with Terminator kind of robots?
You sound very hopeful about it.
What are your plans?
No, just like that. Just wanted to know how long would it take to come up with something as futuristic as that? How long?
I hope the answer is infinity. But
Yeah.
So I think, Bill Gates had this nice quote. I think he said something like, we overpredict the near future and underpredict the far future. And I don't think we're ever going to have something like the Terminator robot, ever. I think we really underestimate how hard it is to do all the things we do so well. Yasser made this point, we're so good at vision, so obviously it has to be easy, But if you do this exercise where, have one of your friends, close his eyes and start saying, pick your leg up just this much, this, that, feel for this. There's just so many intricacies. In fact, what I find interesting about studying robotics is that it makes me appreciate that much more what it is to be, human or an animal or whatever. So I just think this problem is so hard, we'll never have that. However, I don't want to underpredict the future. So we may have something else that you may call a Terminator robot in the future, but I don't see it anytime soon.
Right. And I also actually think it's not even an interesting thing. I mean, it's interesting to Hollywood because it's sort of anthropomorphic and makes for good stories. But if building robots is actually not about robots. It's about making a difference for human society and doing things that make people's lives better. And the kind of things that make people's lives better are robots that are like integrated into our environment. If you look at the some of the control systems in cars these days, you can call them robots. Many things that are embedded in people's homes these days, like the iRobot vacuum cleaners. I mean, those are robots. They're really useful. They just don't look like humans.
Hey, thank you.
I have a question for Dr. Goslin. I was looking at your wave glider, and you demonstrated that there's a cable and a sort of device at the bottom that kind of serves. I'm not sure about how what's the length of that, because is it close to the surface? The reason I'm asking this question, because I come from telecom industry and we have a whole bunch of undersea cables where we have problems where sharks come and chew up these cables and they have to go and repair, and it's very expensive. And if any robot can go undersea and detect these faults and help in the repair, it would be really awesome.
We do that.
Oh, you do? Okay.
But we normally do that by one of those tow bodies and having a camera.
Oh, okay.
And those we can control sort of their buoyancy, how they go up and down. That umbilical cable is an astonishing piece of technology.
Okay.
You'd think it's a cable, it's not.
Okay, thank you.
Thank you. Please.
On the tipping point, the cost of robotic components coming down is one of the stoppers, I think, in making it popular, right? My son, who's a student at this university, bought a couple of robot arms and sent me the bill. Made me go off, made me blink a little. So that is why, what is your thought on how robotic components are coming down in cost and stuff like that?
So in the videos you didn't see, there's these snake robots. Okay, so what's a robot? Something sense, plans, acts. Computers are getting cheaper, sensors are getting cheaper. We're getting better at programming these robots, but there's still the actuator, the mechanical engineering part as well. And what's happening, and what we're starting to see, is there's a trend where we're starting to make modular mechanical components. So instead of having to custom machine a specific piece for a specific robot, we're starting to ask ourselves, what are these modules? What should the modules look like? Because if we can commit to a set of modules, then we can start mass producing them, and that gives the opportunity for cost to come down. Also, if we can commit to modules, we can commit to interfaces between these modules. And that will promote design of other modules, because once we have standards like Ethernet, things will go down more quickly. The question is when is this going to happen on the mechanical side? As early as June of 2015, as late as June of 2035. Everyone's guesses. Yeah, thank you.
Thank you all so much for doing this panel today. It's really incredibly exciting to see all the latest in terms of the applications of robotics. I'm really curious, as you look out 10, 15, 20 years, what thoughts you have on the societal and economic implications of robotics at the tipping point, so to speak. With autonomous vehicles, it may be that truck driver or cab driver cease to be professions. With advanced manufacturing, a whole slew of jobs may disappear. What do you think happens to the economy and to society as so many roles get eliminated?
So Yasser, can you answer that?
Yes, I can. So in the interest of over predicting the future, there's a field of economics I've heard of called robonomics. and this thing predicts that the disruption of robotics is going to be so great that we spend our lives trying to be productive because we want to make income. If we can automate every function a person can do and every function in society, let the robots do all the work, let us do nothing but enjoy, right? That could be one limit of how profound the change will be, right? The question really, I think, is how can we ease into production and automation in a way that complements our economics, it creates opportunities rather than destroys opportunities. I think that the opportunities are going to be profound. That's for sure.
Nathan, do you have anything you want to add to that?
We are looking at a real change in a number of application domains in terms of humans being pulled out of harm's way. So I would say from the perspective of necessarily augmenting or enhancing the capabilities of the individual, aerial robotics is going to make a big difference there. But we still need the role of the human, the operator, guiding that system during inspection, during maintenance, and those types of applications where you have high reach situations, people are put in harm's way. So we are starting to see these types of systems actually being deployed in very real scenarios, but we're not necessarily talking about the replacement of people. We're talking about enabling individuals to work more effectively in a safer manner. And so I think that's a key point there, is that in some areas of automation, it may be a force multiplier and machines can intelligently work, and then it starts to be a concern. But in these particular specialized applications where you are actually very aggressively trying to pull people out of the loop in the situation, in situ, you're basically having them operate on the ground, interacting with the system. And so it creates a much safer situation.
Yeah, it really is all over the map. I mean, for us, we do things that humans just don't do. Having a human out in the middle of a hurricane measuring the hurricane wind is not going to happen. But what that ends up meaning is that we are profoundly ignorant of 3/4 of the planet. But in different areas, it's different. And so if you look at like manufacturing, that's a world that's going through a huge amount of upheaval. But it's been a cascading set of major upheavals for hundreds of years, right? So there was this like gigantic escape of manufacturing jobs from the United States over the last 20 years, and they all went to China. From all over the world, the jobs went to China, where it's helped China a lot, although when you go to those factories, it's more like slave labor than anything else. But there's this interesting swing happening lately that the jobs have actually been moving back because of robotics, right? So like there's a giant car manufacturing facility not far from where I live. It was originally built called New United Motors. And they built cars for Toyota and GM. And that had been shut down kind of forever because all those jobs went away. It was just too expensive to manufacture in California. That factory is now running, at full tilt, it's the Tesla factory. And it's a cool factory to go look in because it's filled with robots doing all of the repetitive tasks that you just can't pay a human to do. So it's one of those weird cases where automating adds jobs.
I thank you. What I'll suggest is in our remaining like 10 minutes left, if we can have maybe some short questions and we'll short answers so more people have opportunities to ask. So,
well, I don't know if mine's a short question, but I'm gonna fire it out anyway. So I wonder if you could talk a little bit about policy in robotics. And Nathan, you touched on this a little bit, right? The FAA has trouble trying to figure out how to regulate drones. The DOT has trouble trying to figure out how to regulate autonomous cars. Automakers don't necessarily want to put things into vehicles because of liability issues. So I guess maybe there's sort of two short questions. One is, how do you get policymakers to be at the same tipping point and maybe be forward-looking? And do you think that policy could get in the way of robotic advancement because the policies just aren't there, and so could prevent something that could be useful from being deployed?
So regarding the FAA, I think the answer is yes and yes. The FAA is at the tipping point. They are taking an active position on this. They're looking into it aggressively, but our government moves at a slower pace than research. And yes, it is slowing down research and advancement. We are not able to test our ideas outside. My projects are focused on inside operation and what is required in order to enable that. Why? Because I cannot fly outside legally. And a lot of people are being challenged on the same front in terms of being able to operate in their own domains for research with these types of systems. From the FAA perspective, they move forward, but I think research will continue to move forward aggressively. I think they're really striving within the next few years to really hit a happy median. Even recently, we've started to see a number of different policy changes to enable the authorized use of these types of systems, aerial vehicles, for a variety of different application domains, where companies have gone, said, we can use these systems safely, and it makes a big difference for our business model, for our safety model, and the FAA has authorized it.
Great, thanks, Mark.
May I actually make one quick comment about this? I think this is actually a really important question to discuss here, particularly when we talk about the tipping point, because the momentum that we're building inside academia and inside the industry in furthering technologies, particularly, for instance, in vision, a lot of capabilities that we're using are going to enable the sort of surveillance that we've never been able to see before, right? And policymakers certainly don't have the sort of momentum and speed that we're making advances in. I think one of our roles as researchers and folks in the industry as well, we have to raise more awareness that it's time for policymakers to really take this up seriously. There are many difficult questions that are going to be, that are already here and are going to be coming soon, and nobody seems to be prepared to talk about them or do anything about them.
Okay, please.
Hi, I work with a consumer products brand that mostly is involved in the health, well-being, beauty areas. Shampoo is not an uncommon product to discuss in innovation meetings, but they have placed robotics on their 15-year macro trend map, and owing to the fact that most of the people in the room are business people and not technology people, how would you put together a program to help them understand the applicability of robotics to their business space? Thank you.
Well, I think it really depends on what it is you're trying to do with that. It's not clear from your question if you're automating the manufacturing of it or consumer use of the robotics. I think you have to, one of the great lessons I've learned over my career is technology creation inhibits your evaluation. Put more simply, creation inhibits evaluation, right? We're a lot of technical people. We're not the final ones who are going to figure all of this stuff out in terms of policy, in terms of legislation, in terms of restrictions on use and so forth. But we have to better understand the consumer who's actually using it. We need business people to better understand how to bring it to market. And there's a huge amount of work to be done in that area for a wide variety of robotic applications. We don't even know all the implications of our own technology, how people will do things. We have a product that just launched. We now have direct communication with smartphones using Bluetooth Low Energy. we're able to actually see really interesting behaviors in what people are doing. And that obviously brings up issues of privacy and security, which we're addressing. But some really interesting behaviors are coming about through the use of this type of technology in the marketplace. So I think having people really understand that. It's not necessary that they be deep in the technology and deeply understand that, but understand what it does. And that's where we can help. That's where we can say, you can do this and this and this. Then that evaluation process can be done. But the technology people cannot do that in isolation. We actually need the business people to help drive that.
Well, and you have to figure out how to make it real for them, how to make it tactile for them. You know, I hardly recommend in situations like that you grab them and you go on a road trip. You know, in my business, one of the things that works the best is we drag people out to our engineering center in Hawaii, and we go for a swim with the robots. You know, you can show all the slides you want, but you get in the water and you swim with the robot, and all of a sudden it makes sense. And figuring out how to explain things to people is an art that takes a long time.
So if we can have just 2 last questions, and then we'll wrap up.
My question hopefully is a quick tangent on Mark's earlier question about drones, particularly the quadricopters, but also potentially like the snake-type drones. You talked about the regulatory aspects, but there's also probably in the last year the public perception, just the general, everyday person has freaked out about drones. Drones are going to be watching my house. Drones are going to be, stealing our mail, or all kinds of very, serious, but also I think, approaches that people will want to block, tell politicians to block this stuff. And I'm wondering how you'd address that to get the general public to be more comfortable and be more trusting of drones when they've been fine with manned helicopters and manned aircraft overhead for decades, and how to translate that kind of comfort to drones.
Trust is a very hard question for the domain, and I think this is a really good question. I personally think that, first off, we tend not to use the word drone because it's more of an aerial vehicle or aerial platform. Drone kind of has a negative connotation associated with it. These systems have an immense potential in the commercial market. And so I think as we see these systems become smaller, in fact, someone had asked about cost. Cost is actually very low for a lot of these systems. You can go out and put down $50 and get something pretty impressive. But consider, for example, if you were playing a video game and you were engaging in airplane flight in the video game, but you were having dogfights where they were not dogfights of actual airplanes in the video game, but real platforms that are small with 2 kids flying them and chasing each other, things like that. You were talking about, as was said, holding the robot in your hand, working with the robot, getting used to the concept of having these systems around you. This is something that's very near term in terms of consumers being able to use these types of systems as an entertainment tool, as something that's fun and enjoyable. They're also being integrated into educational programs, both here at CMU as well as a number of other places. So I think giving people the opposite picture, not the one where they often see in the media or the news, which has negative connotation, but also the statement that these systems bring great promise from a positive perspective, should also help people start to trust that these systems are innovative and will help us become more effective, efficient, and in general operate at a higher quality of life.
Thank you. So our final question.
My question is about computer vision and visually impaired people. Can computer vision is it already being used to help visually impaired, or where are we with that?
Thank you. Yeah, actually there are very interesting breakthroughs happening as we speak. There are artificial eyes that are connecting to the retina. There have been progress. I think 5 years ago it used to be 4 or 5 pixels. These days it's more like 400 or 500 pixels. It's actually connected directly to the eye. Other technologies which I've actually personally been involved with are using the tongue to compensate for vision. But these are absolutely happening, and the place we're at right now is to start using machines to do higher level analysis, higher abstractions, not just is there a person there or not, or is this Phil or not, but also, you know, retrieve memories of what the person means to you, and see if we can augment, really change the social impact of these devices to people too. Not just give them vision, but also help them in their perception of the environment. Because visual impairments and cognitive impairments all often go hand in hand as well. That's really an exciting space, and there's a lot of work going on there. Yeah.
Okay, so I want to thank our provost for attending the panel, and I would like to thank you all for your kind attention with today's event. Thank you. I'm more afraid of you than all.
Actually, Howie, I have to say, great introduction.